Okay, so the problem anybody give a solid answer? Feel good about their energy? Okay. What'd you come up with there, Zach?
Joules per year.
Yeah, okay, that sounds about right. Okay, so it's relatively straightforward, right? So we know, from the first lecture that energy is power times time. Each person on average is consuming 2.5 kilowatts. So we're going to multiply kilowatts times time. So we got 24 hours per day. We got 365 days per year. The days cancel, and we end up with 2.5 times 24 times 365 is 21,900 kilowatt hours per year. That's 78,840 megajoules, or as you said, 78 or 79 gigajoules, or 75 million BTUs, or 747 therms, which you might get into in this course as well. One therm, by the way, is 100 cubic feet. So that means each person on average is going through the equivalent of 74,000 cubic feet of natural gas per year. That's what it takes to run a person. It seems like a lot. It just seems like a lot. 74, let me run the math on that one more time. Let's hit the calculator. And obviously, we use other forms of energy too. I mean, you could convert it to, cubic feet of water flowing through a dam, wind blowing through the wind turbine, biomass, what have you. So 74700 divided by 365 equals, well, it's 200 cubic feet of natural gas per person per day. Okay. Now, what I want to do.
That's 16 cents a person.
No.
You said, the other day you said it was 7 cents once you figured it out.
Well,
Per 100.
I think 100 cubic feet of gas is closer to $10, isn't it? CC, what is
Oh,
the?
yeah.
Yeah.
That's right, you said 10.
Yeah, it's 20.
7 cents was
It's more like $20. Yeah, it's more like $20. And then, so you can then do your energy index and figure out, if it's worth it to be spending that, $20 a day on energy or not. Like how many hours per day do you have to work to buy that much energy? It depends who you are. Okay, so let's do this. Let's, now that we know how much energy it takes, let's just assume, and this is not a valid assumption, but I did say that for a house, you're using about 5 times the thermal energy as you are electrical. Let's just say somehow you've got a cool gizmo at your house. Maybe you've got a little steam engine that could actually make electricity for you so you can make heat. Let's figure out how big a volume of water you need at 100 degrees Celsius, so just boiling temperature. You're gonna keep a volume of water at 100 degrees Celsius. You gotta heat it up somehow, right? You're gonna heat it up with some energy source. Doesn't matter. But how big a volume of 100 degree water do you need to supply all of your energy for a year? I want to know it in liters, gallons, cubic meters, teaspoons. I don't care. But the question is, water at boiling. So we're not going to make steam. We're just going to keep it as hot as we can without going to steam. And I want to know how big that volume of water is. Is it like a swimming pool? Is it the Atlantic Ocean? Does it fit in your bathtub?
Like the total entropy or like the delta T entropy?
Well, you need that much energy. It'll be up to you to figure out what your delta T is. So I would start with 100 degrees Celsius, but then you can just take atmospheric temperature as 20. Just say atmospheric's 20, 25, something like that. So let's do that. Take a little break.
What were the numbers again?
You're going to store this much energy, 2,200 kilowatt hours, 79,000 megajoule. All these numbers are the same. 747 therms. You're going to store that in a volume of water at 100 degrees Celsius. I just want to know how much water that is. And so just give it to me in some reasonable volume. Okay. So the problem I gave you, again, let's just remember where we started. We started with this Shramsky kind of big picture on global human energy consumption. I just assumed that you don't drive anywhere or go to the office, that all the energy you use just comes to your house, and that whole 2.5 kilowatts is per person per house. But it's an assumption, because you're not going to drag your giant hot water tank around with you. That would just take more energy. But we just started with 2.5 kilowatts as a reasonable estimate as to how much energy it takes per person. We solved the problem and went from power, which was 2.5 kilowatts, to energy, which is 22,000 kilowatt hours, 79,000 megajoules, 79 million BTUs, or 747 therms per year. Now, so to turn that energy into heat, this is just the heat capacity equation. So this guy right here, C sub P, is just how much thermal energy a substance can hold. And as it turns out, for water, water can hold 2.4 kilojoules of energy per kilogram for every degree Kelvin it raises, or for every degree Celsius it raises. So all I did, I started with this equation, and I used mass is equal to density times volume, right there. C sub P stayed the same, delta T stayed the same. And then, since I know I'm trying to find the volume, I just solved the equation for volume. So I threw energy over on the right-hand side, threw volume over on the left-hand side, or just reverse the sides. It doesn't matter. The equals sign is symmetric, but it's conventional to put your unknown value on the left. Everything else you know on the right. So what did I leave out here? C sub P. Oh, no, I didn't leave out M because I got rid of M. I replaced it with rho and V. Okay, so what I'm left with is the volume is equal to how much, and let's just walk through this. So if I need more energy, I'm going to need more volume. It's just, straight up mathematics. They're both in the numerator. If I can have more energy per unit mass, I'm not going to need as much volume. So if this got bigger, and I think you might have heard of like salt batteries and that kind of thing. So like salt, I think the heat capacity of salt water is more than just straight up water. So you could get creative here with a better fluid than water. But for now, we're just using water because it's everywhere. I got frozen chunks of it laying all over my house. And this is the density of water. It's 1,000 kilograms per cubic meter. There that is. And then I said, let's get to 100C, which is boiling, just right at boiling. I don't want to make steam, but I'll get as close as I can to steam without going there. 20 degrees Celsius, that's average, 50, 60 degrees, somewhere in that range Fahrenheit. Okay, so from here, it's just plug and chug. So I popped it into Excel and divided. Where'd this thing come from? 80 million kilojoules, is that correct? Well, I had 80 or 78,000 megajoules. I just called that 80 million kilojoules. So that's what that is. 1, 2, 3, 1, 2, 3, 80 million kilojoules. And I went out and looked up the thermal capacity of water. Indiana University gladly supplied that. 4.2 joules per gram or 4.2 kilojoules per kilogram. Same difference. Uh, 4.2 kilojoules per kilogram Kelvin. The density is 1,000 kilograms per cubic meter, and I'm going to heat this water up 80 degrees Kelvin. Now, there's a lot of ways to do that. We actually last summer, and Shauna was there, she saw it. Practicum? Not yet? We just unwittingly boiled water in the sun. We had this solar collector, we had water inside, and all of a sudden the thing just exploded. It's like it wasn't supposed to explode, it was just supposed to make hot water. But we designed it in such a way that, I don't know if I don't have a figure of it, but I'll just tell you, we designed so normally in a solar thermal application, and you guys have all seen a radiator before, right? Typically in a radiator, you've got a bunch of tubing that goes, back and forth like this. The cold stuff comes in here, the hot stuff comes out here. Well, we just, because it was easier, so we didn't have to put so many tight bends in our tubing, we made a radiator look like this. So we had cold coming in here, we had hot coming in here, and we got the energy from the sun. We just stuck it out in the sunshine, and nice black tubing with a bunch of water in it, likes to soak up photons, no problem. So normally you would get fluid flow, heading right on up. And as fluid gets hotter, obviously it becomes less dense fluid goes to the top, et cetera, et cetera. In our case, we had this issue where it came in cold from a bucket, and the idea was to come out hot. And what do you do with hot water? Well, you wash dishes, you take a bath, you do the laundry, lots of uses for hot water. But what happened, we had these little hot spots at the top, cold spots at the bottom. The fluid did this, in each one of these little loops, steam. Kind of cool. So didn't mean to make it, but there we were making steam because it just actually blew our system. It was kind of cool.
Did you have the top capped?
Nothing was capped. There was just enough, again, pretty small tubing. So we could even, and I didn't throw, I didn't want to get too crazy today and actually throw thermal energy into that Bernoulli's equation, but you could imagine, putting thermal energy in there as well. It's got to go somewhere. Once it boils, it's going to expand. Once it expands, it's going to make pressure. Once it makes pressure, it's going to move. So it's still related, but
That's
yeah.
where you do that. It'd be like a water hammer in a boiler because you had the water.
Yep.
You had the heat, it vaporized it, which created air.
Yep.
When they came together,
Bam.
that was the force.
Right.
And that's what split it up.
Yeah. And it was actually,
Electrolysis or whatever.
well, we weren't quite to electrolysis. I mean, we weren't pumping electricity in, but we were hot enough to make steam and, blew
It's a water.
the tubing, yeah. So anyway, 80 degrees is our delta T. And so from there, I just came up with 240 cubic meters of water. So, well, is that a lot? I mean, it kind of sounds like a lot of water. But from there, I just went and took the cube root. So one way to take the cube root in Excel is to take a number to the 1/3 power. So all I did there is I took that 238, which is in cell F2, to the 1/3 power, and I came up with 6.2. So going back to our problem of making hot water, the cube root of 238 is 6 by 6 by 6 meters, or 20 by 20 by 20 feet. And that's not that big. I mean, that's about the same size is that house we did with the hot air and the 6 cents worth of heat in it. So really, now, all you need to supply all the hot water you need for you to exist for a year is your house underground filled with 100-degree water. So, there it is.
55 degrees, doing the ambient, depending on if you're using ammonia, expansion, contraction, you've got ambient heat, so you're going to take the heat one way or the other.
Mhm.
So you've got 15 degrees all the time.
Mm-hmm. Yeah, and now obviously, this is just for, bathing, showering, cooking, laundry, but, if you're, and I don't know how, do you guys get into some of the math on construction costs? Like what it costs to make, so you can do the math on that. You could then sit down and say, what's it going to cost me to build an insulated structure underground that's that big, right now in today's dollars, and what am I going to save down the road by getting rid of my natural gas heating cost if I can, again, just store that thermally. So another problem for another day, but it's something that's doable.
So we can construct the field, but not necessarily whole systems.
Yeah. So anyway, something to think about, down the road. So that is really about all I had to cover today. We went over fluid statics, fluid dynamics, phases, did some Bernoulli, and then that heat transfer technology. The only thing missing from that little problem we did was just what kind of pump you use to pump the heat around. Obviously to do that, it's going to take a little bit of energy too, but well, there you go. Anything else before I let you go? I'm thinking we'll see some quiz questions on this in a couple weeks, but other than that, thanks a lot.